Hi everyone. Today I have an ambitious task ahead of me. What I'd like to do is extend on a previous video in which I modeled event data using a number of techniques and expand this to basically the spatial domain, which means I'm going to skip over some things and I'm going to introduce some new things, and I'm going to try to do it all in 10 minutes, so we'll see if I can pull it off. So the first thing I have to do is create the data, and what I'm going to do here is go through the similar process that I used in a previous video, except I'm going to turn these data into spatial data. So here I've now got a spatial points data frame. These are a series of points that have spatial meaning, coordinates, and a lot of the other structures in it that allows you to apply certain methods or certain functions using some of the spatial libraries, or spatially relevant libraries like these ones here. So I've created the spatial points data frame, and the next thing I'm going to do is actually create a Voronoi tessellation, because I want polygons. This isn't absolutely necessary, but I think for visualization it works a little bit better. So these are polygons. Each polygon has data associated with it that I will add in. So here we go. I've got polygons. I'm going to add data. Here I've got what I'm going to call just a risk factor. So this is something that you could use to predict the frequency of some sort of event. So I talked about in the last video, imagine if we were trying to predict crime, we could maybe treat the risk factor as unemployment, let's say. And then we're going to create a true rate, something that we wouldn't typically know, but this is kind of the rate from which we're sampling data. We're going to be creating data. The true rate, it's going to be a function of this risk factor and some random variability at this stage. So I run this code here. There we go. And then the next step, I'm actually going to map this out. I want to see what this looks like. And so I'm not going to describe how I do it. You can see it in the code if you want to do it yourself. I'm just using a little strategy I use to, it's a simple plotting strategy you can use in R. This kind of, you can generate kind of a standardized looking thematic map. And so what we do is we see the predictions of, let's just say, crime, where the dark green is higher crime and the light green is lower crime, based on this model. Now, to make this example more interesting, what I actually want to do is add some spatial correlation structure to these data. And the way I'm doing it is probably not the best way. The truth is, spatial patterns can emerge for lots of reasons. And the way I'm synthesizing it in this data set is somewhat unrealistic and maybe not particularly sophisticated, but I'm going to do it anyway. Basically, what I'm doing is going to take averages by passing a window over the data and taking these kind of weighted, these averages and kind of smushing the data together. And you can see the consequence here is that we get a pattern emerging, a clustering in a number of different areas, where areas with similar values are kind of squished, are neighboring each other, right, in the following way. Now, I don't know, it could be that some spatial processes do work this way. I'm not sure it's the best way to do it, but it doesn't require a lot of code, and I kind of wanted to keep this simple. So now that we've got this pattern of true risk of crime generated, I now want to basically complete my creation of data by creating the number of events here, as I've done it here. Now I want to model the data, and for the first 3 models, I've done them before, so I'm not going to talk about them at all. I did them in the last video. So basically, the first three models are using the same approaches that I've used before in an earlier video. And then I'm going to try a 4th approach. Now, the idea here is there are a number of different ways you can model spatial data. And how you do it depends on a number of things, the structure of the data and what you think the process is that actually creates the spatial pattern. The strategy we're using is this conditionally autoregressive model, or CAR model, and you can read up on it here. It's somewhat less flexible than alternatives. This is the package that I'm going to use to estimate it. And the actual original literature goes back about 30 years, and I'll show you a reference for that in a second. In order to actually run this model, I need to create a spatial weights matrix. Now, earlier on, I didn't actually show you, but I created a list of neighbors, and if you look at it, I ran the code and I didn't actually discuss it, but basically this is a list of neighbors for each polygon. So for the first polygon, its neighbors are polygon 3, 14, 16, 26. For the second polygon, 5, 28, 34, and so on. So we basically have a list of those neighbors. And what I want to do is turn that list into a weights matrix, a very simple weights matrix. And what this weights matrix looks like, it basically tells you which polygons are neighbors to which, and it identifies them with a 1. So here, this tells us that these two polygons, 1 and 3, the first polygon and the third polygon are neighbors, and we know this because there's this 1 here. And we see it here too, because it's symmetrical. So neighbors are 1s, non-neighbors are 0. Okay. Now with that, this is not necessarily the best way to do it. I'm just kind of coming up with a nice simple example. We have a weights matrix. With this weights matrix, we can now try to estimate this CAR model using this BYM strategy here, which well, it's rather involved, but the reference for this work is Baseg, York, and Molly, 1991. This is a particular strategy for modeling data, and we can use this particular function, because it's available in R, to do it to estimate this spatial model when our outputs are when our dependent variables account. So we can use this generalized linear model, this Poisson regression model, and make predictions that are spatially informed using this approach. Now, if I run it, it's going to take a second to actually complete it, because it's using this Bayesian strategy for estimation, for understanding or building the structure of the model. And it takes a minute because you have to do this burn-in, and there's this kind of resampling process involving that you see in Bayesian estimation. And then once it's completed, I'm going to go through the same process that I used for the other models to generate actual predictions from this model. And then we're going to plot out these predictions here. Now, the process that's driving the pattern we see in this map, because of the way I created it, is actually very spatial. I've really, much of the pattern is dominated by, it's dominated by a spatial process of some sort. So it shouldn't be any surprise when we see the plots of the relationship between the true rate and the rate that's predicted, that the spatially informed model, the one that takes into account, to speak very generally, the immediate neighbor's impact on a given observation of the dependent variable, you can see that the relationship between these things is much stronger for the spatially informed model than for the other models which have no spatial information in them. They're just models influenced entirely by the dependent variable that I've imputed into them. And then if we want to look at that sum of the squared error, so between the known true rate that we've created and these predictions, we can do it this way, the same way we've done it in earlier videos, and you can see that it's an order of magnitude better. When you've got such a clear spatial process going on, to ignore it is to lose a lot of predictive power in the data, and you can see that the spatially informed model is a lot stronger. I happen to find that in the real world, the spatial effects tend to be weak, especially for a fully specified model where you've got lots of other information in it. But there are exceptions to that, and I think it's worth keeping in mind that when you know there's a spatial process that you're not accounting for with other variables in your model, it's wise to think about the idea of a spatial model. There's a lot of literature on this, and picking the right spatial model is no trivial task. And so, in spite of the fact that I've shown you how you can do it, that doesn't necessarily mean this is the best way. It might not even be the best way to do it with these data that I actually created here. But it is a strategy, and it gives you a kind of a cursory sense or perspective on how one might model spatial count data that have some sort of underlying spatial autocorrelation or spatial dependent structure. I hope that was useful. Take care. Bye.